Uh, Good evening, everyone. Welcome to the online session uh, of NPTEL course Water and Wastewater Treatment that is being taken by instructor Professor Bhanu Prakash. He is from IIT Roorkee. My name is Manitnam Prakash, and I am here as a part of my TA duty. So, welcome to the week 7. So this is as usual. We meet every Tuesday from 7 p.m. to 9 p.m. and we use this link. So in week 7, these 5 topics were discussed. That is water demand, water quality parameters, overview of water treatment, physicochemical treatments, and coagulation. So some of the part was already covered in the first lecture, and this was like till now we were discussing about wastewater treatment, like primary sedimentation tank, then tertiary sedimentation tank. Then we discussed about this thing, what do we call how to reduce BOD, COD, nitrogen removal, and phosphorus removal. And we seen different type of different type of bioreactor, that is activated sludge process. But after that we are discussing about the drinking water. So every household that we see, every city in a society we see required some water demand, so required some water. So there has been some empirical formula given that per day how much water should be given, all depend upon the population of that area. So I hope you have already gone through the lectures. If time permits, I will be discussing those formulas also. But then we discussed about the water quality parameters. So water quality parameters such as alkalinity, we follow the IS code, that is 10500 2012. So whenever a water is being supplied to any household or any society or any location, so it should meet some water quality parameter. And that water quality parameter in India is checked by IS code, that is Indian standard, that is being made by BIS, that is Bureau of Indian Standard, and the name of the code is 10500 2012. So I think as an environmental engineer, one should have a proper idea of what is this IS code, and he or she should at least remember what is there is two limits written there: acceptable limit and permissible limit. So one should have an idea that what is the different parameter required, that is essential for drinking water, and what are their limits. What permissible limit that should be present in water, and it should not cross that limit, because if any parameter is crossing the permissible limit, then that water will be treated as misconsidered as polluted water. Then we discussed about the overview of water treatment, which was similar to the wastewater treatment, but there were some different units. Like in normal water treatment, we do not use this secondary, tertiary treatment, or secondary treatment like biological treatment and all these things. It's just a simple. Okay, then we understand the concept of physiochemical treatments, like what is the effect of pH and miss pH and different parameter when we add, because in water treatment we simply just add some chemicals, and we see how these chemicals interact with contaminants present in the system. Because see, in if you have gone through the lecture, this water which we are supplying or which are being treated, are either taken from the groundwater or from the river. So those rivers do not contain any kind of organic matter. Most of them are inorganic pollutant, and most of them are in dissolved form only. There might be some biological, but that is another thing which I will be discussing in the last today's last session. That is mpn and all these things, that is different thing. But apart from that, there are some inorganic contaminant which should be removed, and there are some suspended particles that has to be also removed. So we add some chemicals, so that chemicals will only act in a particular pH system. So we have also seen that how this physio-chemical treatment happens and all this thing. And last we have discussed about the coagulation. So there are three parts: sedimentation, coagulation, and flocculation. So we have in this in week 7 just we have discussed about coagulation, but in further lecture you will be more focusing on this coagulation, flocculation, and then last sedimentation. Okay. So again I will be discussing some of the important questions related to all these five topics, that is water demand, water quality demands. There are total 10 questions, so I will be going one by one. If you have any kind of doubt, you can raise your hand and ask me. And so I will be moving forward. So the first question is of see in water demand, the most important thing is that how much water is needed depend on the population of a city. Now imagine you are and why we need to study about the population of area. So it is needed because suppose you are constructing one water treatment plant currently which has population say X. With time it will increase, and it will go to maybe say 2x, yeah, 1.5x. So obviously the water demand will increase. So you cannot design any treatment plant for current population. You have to design your water treatment in such a way that it can fulfill the demand of upcoming futures also. May say you have may it may you may assume that you will be designing your water treatment for next 30 years. So you should know what is the projected population, yeah, expected population that will be occurring in uh, next 20 years, that is at the end of 2030. So there has been several empirical formula means people have tried to mathematically derive some formula also, but some of them has given empirical formula also. So for example, let's see there means and how means how they have modeled the data. So they have recorded they have the census data of previous decades. So we know that every 10 years there is one what do we call census. I mean, there is countings. There is particular term I am not remembering it. So people number of population for a particular area we know. So from past population we try to develop some model, yeah, some progression that how this population is increasing, and based on that we try to predict the future population. Okay. And why we are predicting, our main aim is to our main target is to design one water treatment which can fulfill the demand of current population also, and for next 30 years also. That's why it is essential. So wherever you will be studying this thing, water demand, the first thing which is being discussed is the population, like how population of that particular area will increase. If you are aware of that population, you can easily design means how much means. And from the population, what we want to know, we want to know that how much water I have to supply to that area. Okay. So this is the first question, that census of a data. So five 1 2 3 4 5 for last 5 decades the data has been given, and there are total 5 set of questions based on this data. So we'll be going those questions in one by one. So the first question is, calculate the projected population of village for the 2023 using arithmetical increase method. So I have already said there has been several method designed for estimating the population. So one of the most simple, which is generally not used, remember this is not used, this is just a most simple arithmetical increase method, because it has been said, generally it is said that when the population of area is very small, then this arithmetical increase method can be applied, but when the population of any area is very large, then this model is not applicable. So this is limitation of this increase in arithmetical method, so we generally don't use. But suppose in examination someone is asking you to project the population of an area using this arithmetical increase method, then you should know the method. It doesn't matter this method works or not, it's separate thing, but you should have an idea how this arithmetical increase method work. Okay. So generally what is happening then, when arithmetical increase method is defined as the population of any particular area is just increasing constantly with respect to some constant value. Okay, that is dp by dt is equal to k, means it does not depend upon the current population of the system, this is assumed. Okay, so dp by dt is equal to k1. So if you integrate and put all the initial value, you will be deriving this equation, that is p naught, that is population after n is decade, after n decade will be last known population, p naught is equal to last known population, and n is equal to number of decade, and x is the average increase or decrease. So remember what will happen, that population of any area will either increase or decrease, so you have to take the average of that increase. Okay, so what is this increase? So initially suppose in 2002 there was the population was p1, and in 2020 2012 population will be p2, so either it will be increasing or decreasing. So x1 will be p1 minus I want to, so x1 will be x1 will be uh, p2 minus p1. Okay, so this will be x1. Similarly, suppose if here I have 5 data, so if from here I will be getting x1, from here x2, from here x3, and from here x4. Okay, so I will be getting this increase in, and it will be divided by, we will be taking average, because if 5 data is there, differences will be only 4, so n minus 1. Okay, so this have already I have written p1 minus p naught, and n is equal to number of decades, this I have already told you. Okay, so based on this basic information I will be calculating these things. Okay, so we already know that Pn, well, that is population after n decades, is equal to last known population plus number of decades into number of decades, means after how much decades I want to find the population of that area, into increase in average. So how I have calculated x average. So our population was this thing, that in 2000, in 1971 it was this one, and with next 10 decade, with next in next decade it was 571, in next decade this. And so what we try to find, try to find our x value, that is increase. So it will be this minus this, it will equal 127, then this 724 minus 574 is equal to 150. So total I have found x, this is x1, x2, x3, x4, 1 2 3 4, sorry, this is average, this is everything. Okay, so this x1, x2, x3, x4, and I have taken average of these three things, and it come out to be 2000, sorry, 215. So now remember, the last known population was 2012, 2011. So and I have to find the population of 2023. So how? So we know that one decade is equal to 10 year. So it is asking to find the population after 12 years. So so the number of decade will be 12 divided by 10, so that is n is equal to 1.2. So if we substitute the value, we will be concluding that population after this in 2023 will be sorry, actually I should not write in here. Okay, now this should be year, because if I am putting in 2023 here, it should be also here. So it is this should be not be in. Okay, this should not be in. I will just omit it. Okay now. Hmm. So just I am saying that population in 2023 will be initial last known population plus 1.2, that's the number of decades into average, and it will come out to be 1565. Okay, so this is my final answer. I hope this is clear to you. So now the second method is known as geometrical increase method. So now we have already seen arithmetical. Now they are asking to calculate the geometric. Again, this method is not applicable in current scenario, because this has also some kind of limitation. It is like when it won't work when the population is very high of particular area. Okay, so here what happened that it is saying that increase geometrical increase method means the population at any time is increasing is depending upon the population of that current location, means at that time. Okay, so if we again integrate all the value, and if we do this some permutation, some what do I called, keep put the initial condition and do some um, mathematical expression here and there, then you will be getting this value that p naught population after some decades will be in last known population plus 1 divided by r by 100 into की power n. Okay. Hmm. So, so this is P naught is known as last known population. R is equal to average increase or decrease, and there we have as it was in arithmetic method, so we have taken the average. But here, as it is geometric method, then we will be taking the what do I call, this geometrical mean. And we know that how this geometrical mean is calculated. Here I have made one mistake. It will be m. Here it will be m. Sorry. So we are taking the geometrical mean, and we know that geometrical mean is given by this formula, and this R1 will be calculated by P1 minus P naught. That is population of next decade minus previous decade divided by previous decade. And this is what is this P1 minus P naught? We have already calculated in the arithmetic mean, that is known as X naught or X1. You can say anything. It all depend upon you that how you want to represent your data. And then n, we already know that this thing. So from here you can see that the population was increasing in this manner. So increase average increase, sorry, average increase will be this minus this minus this minus this, and r, how I have defined r I have defined as x1 divided by p naught. Okay, so here I have taken sorry, so I have divided so what do I call, and remember I have taken this thing, no, it's correct. Does I have taken percentage? Here I have taken percentage. Okay, now R I have calculated in by multiplying it by 100. Just so this minus this, it will be 127. 127 divided by initial population, that is initial population, that is 127 divided by 447 into I have multiplied. Remember this is R in percentage. Okay, so I have calculated and I have taken average of this thing. So so the population after n decade will be initial population, last known population 1 plus r by 100 की power n. So p naught will be 1307. We have already know this last known population. Average increase in degrees come out to be 30.6. N is equal to 1.2. So I will be substituting all the values. Okay, again I have made one mistake. It won't be here 2023. Okay now. So why, and I have substituted the value, and I can remember the population is always reported in some integer. So if you calculate it, it will come out to be 180055. So I will be reporting to the next integer, not lowest integer. I will be always reporting my answer to next integer, that is 1801. Okay, i hope this is I hope this is clear to you. Okay, so now they are using, they are asking to calculate the calculate the population using the incremental increase method. Okay, so this is little bit uh, latest type of modeling. People have used various kind of method, and they have developed this technique, developed this method. So I will be directly writing the formula for the incremental increase method. They give the formula that population after n decades will be last known population plus number of decades into increase in increase in increase or decrease in population, average of increase in decrease, then n into n plus 1 divided by 2 into multiply by average. What is by average? I will be writing here. So P naught is already know that last known population, X average we already know that, and X1 will be population of first minus next decade minus last decade. And now they have defined one thing by naught by one, that is difference in increase in or decrease, difference of increase or decrease. And y average is they have decrease, they have defined as average of increase or decrease of this thing. Average, they have taken the average of average, in that way they have defined it. Okay, so they have seen some kind of relation, and empirically they have not empirically, if you miss do the calculation, some kind of calculation, you can derive this equation also depending upon the data. So here what they have done, we know the population, they have calculated x, and y, how they have by, they have calculated by they have calculated by dividing x1 minus x naught. Okay, so and they have calculated, now you can calculate this average. X average will be given by the average of this thing, that is 211, and by average will be given by this thing, that is average of these things. Okay, just 1 minute. So you can calculate the population in 2023, that is last known population plus 1.2 into 215 into by substituting formula and taking the average, and you can see the, you can report your answer as 1656. Okay, so by using in common in your in BTech study, yeah, in gate examination people are asking question related to these things only. That is either they will be asking question on geometric, arithmetic rarely, I think they have never asked. They have always asked question on incremental. I think they have asked only once, twice on this incremental increase method. Okay, so this was third question. So they have, now what happened that they have defined one term. They have, the next question is the method which has growth ratio ranging from 1.2 to 3 point is to be selected for forecasting. Which is the following method has the growth ratio in that range. So we define growth ratio in by population of present year divided by population of base year, means population of your projected divided by population of current, that is base year last known population. So now they have said that for treatment plant, they have decided that when they will be designing their treatment, they will be taking a growth ratio of 1 is to 1.25 to 1.3. Okay, so you know the which population, because you are now you have three option of population, that is one we got this thing, mm, sorry, one we have got 1565. From second method I have got this 1808, and from the third method we have got 1656. So in design, when you are designing, there is something written that you have to take this much ratio. So now depending upon the your calculation, and you will be finding the growth ratio, and here it is written in arithmetic population. See, in 2023 the ratio in different method we have got this, and in 2021 the ratio was only the population was same for all three cases, that is 1307, 1307, 1307. and we calculate the growth ratio, that is 1.2, 1.38, and 1.27, and they are asking to choose between 1.25 to 1.3. So we will be choosing this ratio. So for our design purpose, I will be considering the population as 1656. Okay, so my answer, correct answer will be increase. See, remember, they are asking just simple question, but when you will be designing your water treatment in real case, you will be facing the first step. This thing will be your first step. So you will be actually these are three basic method. I will be explaining one more method, that is logarithmic increase in population. People are using logarithmic, like it has been seen that none of these method has been applicable in real world scenario. The growth which is being seen currently is following logarithmic growth. That is, I will be explaining in the next slide. But still, we are using conventional method, and we are following these method, and out of those method we generally rely on the growth ratio for designing our parameter. This growth ratio is being taken, and based on this result, so I will be, for my design purpose, I will be considering the population of 1656. I hope this is clear. The question was simple, but what you are interpreting from this question, you should understand what you are learning from this question, that why we are finding growth ratio. Okay, this is most important. Okay, I hope this is clear to you. Sorry, the answer is already. Sorry for this animation. So now there is one question of fire demand. So remember, when we are designing population, apart from the water which is being for given for drinking purpose, bathing purpose, cleaning purpose, apart from that, a separate amount of water is being conserved or reserved for fire, because in any particular area there might be fire at any time. So we cannot use the water which is being supplied to the residential area. So what is happening, it is suggested that you should always keep a reservoir of water that will be always used for fire. So that is fire demand. So there has been several formula. One of the formula is Kuchling's formula, and the formula is given by this is purely empirical formula. There are several formula. If you go through the fire demand, you will be finding many formula. So I think those formula, use one should have an idea what are those formula. People ask directly based on ask question based on those formula. So it is said that fire demand is given by 3182 under root P. Okay, now remember, here you have to use P. So remember how, which P I have should be used, all depend upon the growth ratio. So P for the we know that I have to use for incremental increase method. So P in 2023 was 1656, and here P is taken in thousands. So I will be dividing it by thousand. So it will be 1.656. Okay, I will be substituting here. So fire demand will be this much liter of per second. Okay, so suppose if anywhere some water some fire outbreak has happened, so this much amount of water will be required, depending upon the intensity of the fire, means how much time it is required. So there has been several studies about fire demand, have several method in doing design of any building or doing that is separate thing, I won't be discussing it. So you should have an idea of, apart from the normal demand which is given to the residential area, a separate demand is kept, that is fire demand. Okay, so that any kind of what do we call fire hazardous can be tackled. Okay, so as I was saying that, apart from um, apart from all these three method, right now people are using logistical model for population growth. So it has been seen that population is not growing arithmetic. How, when we are saying arithmetic, how we are saying that it is increasing linearly. When we are saying geometrically, we are saying that it is increasing. Just remember, I will draw it. So when we are saying that it is arithmetic, we are saying that population is increasing in this manner. When we are saying that population is increasing in geometric method, then we are saying that it is increasing in this manner, or this manner. And similarly in incremental method we are saying it is in between these two, but it has been seen that population increase in this manner. So there will be some initially there, see what did I say, initially what happened that population is very low, so it will follow this incremental arithmetic method. As soon as population will increase, it will follow geometrical increase method, and with more number of increase in population, there will be decreasing rate of increasing method, and finally logistic growth method. So yeah, finally, if you plot all this equation on a plot, you will be getting this kind of population. Okay, population graph. So in this formula, it is saying that P is the population at any time. L is the limiting or carrying capacity. Remember what is limiting or carrying capacity. When we say that this area is populated, yeah, this area is very high population. India is very high population. So how we are defining, means what is the main criteria, like that why you are saying that this area is to very the number of population in this area is very high, because every area has some limiting capacity depending upon the resource available, water resource, in resource everything. When we talk about resource, the availability of water, land, job, and all these things. So depending upon all these things, a limiting criteria is defined for that in any particular area. If the population of that area is crossing that limit, we are saying that that area is populated. Okay, means highly populated. Miss, you can, I don't know the limiting capacity, limiting population of India. What should be what should be the limiting population of India? But it is said that it has crossed very high. Means it has double the limiting capacity. So, miss, exact number I don't know what is the limiting capacity, but you can always check for any particular area. This data, I think somewhere it is given that this area should have this much of population. So if that area is crossing that limiting population, we will say that that area is populated. Yeah, this area has very high population. Okay, and K is constant of proportionality. Okay, so I hope this graph is clear to you. I will be just reading out some material which is I have taken directly from book. Okay, and this thing are written same thing which I have already discussed to you, which I have already discussed. So, consider a population growth in a human settlement or colony occupying a specific geographical area. So, now remember this there was a open area which was not, there was no population. Now, people has gone, humans have gone there and started to occupy that area. So, initially, only a few plots or residents are occupied because of lack of development of infrastructure facility in that colony. So initially, what will happen? The number of population will be very low because there is no infrastructure, no development. So obviously, people will start this thing. So sometimes this is also called lag phase, because people will be start adjusting themselves in that area. Okay, so it is not attractive place to live in, and the number of residents will go. Now what will happen that suddenly the population will start growing. People have started to. Um, People has started to settle there, so there can be up to there will be increase in population due to two reasons, either due to reproduction or due to migration of outsider. So initially what will happen that the population growth at any time may be considered as arithmetic. So remember, when I was discussing the first question, I was saying that this arithmetic method is generally used when the population is very low. So initially you can see the number of population is very low, so that's why it is a arithmetic increase. Okay, and the population will be governed by this equation. Now once this, oh, whatever. Okay, once this once this phase one this limit has crossed, means there is significant amount of population. So now once the population has reached a certain level, the infrastructure facility develop rapidly to serve the growing population, and the places become attractive place to live. Eventually when the number of population will increase, there will be a infrastructure grow. People will start coming from outside to that area. So eventually there will be increase in population, and that is governed by this geometrical population. Okay, geometric, that is dp by dt is equal to k2 into population of that particular time. I hope this is very clear to you. After geometric growth of the population in colony for many years, remember now this is occurring for many years. Okay, this will keep happening. Okay, the colony begins to get congested. Now what happened that as population has started to grow, infrastructure has started, people will start occupying the resources of that area. People will start building homes, offices, companies in that particular area. When we say increase in population, we just don't say increase in population. Always remember, we talk about the infrastructure growth, company growth, um, many things that will highly impact your resource. Okay, the colony begins to get congested and almost all houses or plots are occupied due to congestion and the lack of share of space. The population growth in the colony slow down. Initially what was happening that there the growth, you can see that there is a high growth rate, means population is within this short time, say from 30 to 70, the population has gone from this 20 to around 80. Okay, remember this dpe by dt is increasing the rate of growth, not number of population. So the rate of growth is has increased during this time very rapidly. But what happened that once this area has get congested, it will get slow down. Okay, so this is known as decreasing rate of increasing, decreasing rate of increase. Decreasing means there is increase in population, but the rate is decreasing. Okay, at the rate which it was supposed, yeah, which it was happening, it has decreased, and the phase of that population is known as this thing, dp by dt kl l naught minus this, sorry. Huh. uh, so just one minute. Hmm. So this dp by dt is known as kl minus p. Okay, where L is this your limiting population. This should be always, one should have always the control over this L. If suppose any area is controlling this L thing, that what is the limiting population of that area, then the resources of that area can be managed in very well manner. In India, the problem is people are facing water scarcity, land scarcity, agriculture scarcity, just because in India the population has gone beyond the limiting capacity. Okay, so for your own knowledge, yeah, for your own interest, you can just go and check what is the you can, I won't ask you to go to look out throughout the whole India. I want to just to go and look at your own city, yeah, or village, wherever you are staying. Just check how much population should be there and how much population is there. Is it has crossed the limiting criteria? Then you can say that your area is populated very much, the population of your area is very high, and people will suffer now, right now or after some time, but people will suffer due to this increase in population, because resources are fixed, the water are fixed, land is fixed, and population is increasing, and there is no way to feed those population. So this is the best way to check. Okay, I hope this was all about these question were previous year question, and this was I added from my own class notes and all this thing. Okay, I hope this is clear to you. If you have any doubt, you can ask, or I will go to the next question. Okay. Just one minute. Coming to the next question, which is very simple question, which has been discussed many times during this discussion. Okay, the match the typical water quality parameter. Remember, Really, in every college, yeah, every university, this water and wastewater treatment are being taught simultaneously in same semester. So what happened that either someone will teach you water treatment first, then wastewater treatment. The the basic concept which is required in the both treatment are same. If someone is using sedimentation tank is used in both water treatment and wastewater treatment. The addition of some chemical might be different in both the things, but the basic concept is very similar. So what happened that generally when I was studying here in IIT Kanpur, so what happened that first I was taught water treatment, and when water treatment was taught, every unit that are present there was discussed, like primary sedimentation tank, then filtration, slow sand filter, and all these things. One and once this was over, the wastewater treatment was started, and only one thing was seen that if you want to different unit was said that for treatment of wastewater these units are used. The common units was not being repeated. Obviously, there is no point of let's see what is the answer. Huh? Yes, you are right. So I will discuss one by one. The first is chemical. Okay. So first chemical, what we add some chemicals to remove what will this chemical do? It will react with something, and it will react what it will react with what. It will either react with some of the chemicals that is already present there, and that chemical or some kind of salts that is already present in there. So salinity is due to I hope everyone is clear with what is salinity. It will be due to salt, some kind of salt. So Na, sodium will be there, magnesium will be there, and hardness is also due to calcium and multivalent ions, all the multivalent ions, that is sodium, magnesium, aluminum, iron, all will lead to this hardness. So we will be adding some chemicals to remove those things. Then heavy metals such as this is if we are talking about heavy metals, then it contains some kind of chromium, arsenic. So obviously to remove those things we add some kind of chemicals. So obviously the first one will be matching with the D. Okay. So then then it comes physical. So in physical what we do that we use the no, not talking about sodium. Obviously sodium is not multivalent. Hardness I said due to multivalent ion. Salinity, when I was talking about salinity, then sodium I was talking about sodium. Hardness is only, yes, you are correct. If I have said such a statement, then I'm sorry. But hardness is only due to multivalent ions that has valency of more than 2. Multivalent cation, yeah, remember, not anions, only cations, that is Mg2 plus, Ca2 plus, aluminum 2 plus, iron 2, iron 3 plus, those three. Okay, I hope this is clear. If I said something like that sodium, then I'm sorry. But salinity is due to those salt, and salt will be generally in form of NaCl and all this thing. Okay, then we come about the physical method. Then physical means physical. What will happen that we use some kind of initially we use some kind of aeration tank so that sufficient oxygen can be sufficient oxygen can be given to the system, so that if generally in wet water, the in water, groundwater, the organic matter is very less, but still if something is there, it can oxidize. Or so what happened that this physically is used for removal of taste, odor, and temperature. So some external mechanism is also used to control the temperature of your water. Okay, then there is this thing biochemical, which we have already discussed, that this is to remove BOD, COD, TOC is total organic carbon, and this BOD is biological oxygen demand. Okay, so this is biological miss. What happened that we use some kind of organics and all these things which we have already discussed. Then last thing is microbiology, that is related to pathogens, volatile suspended particles, or viral particles. Okay, so if Hmm. I think I said something wrong. Just let me check. Hmm. Actually, they are talking about the physical. I was discussing about the removal process, but they are just talking about the physical water parameters. So this was just a simple. Biological will be due to some kind of pathogens and all these things. So obviously the answer was C. Then when we talk about the physical things, we talk about taste, odor, temperature. I hope this is clear to you. Okay. So now remember, all these parameters can be tasted, and people do taste. Order is day. And remember this question, remember one more thing, this BOD is not a water parameter, so this should not be here. I don't know how actually this, I have copied this question from somewhere. BOD, COD and DO are all are best water parameter, are not water quality parameter. Okay, organic carbon will be there, but this BOD is absolute. So if someone will ask you what is the BOD in drinking water, then you have to say this BOD is not defined for drinking water. This is defined for what do we call, only for wastewater. Okay. So because BOD represent the degree of population pollution of organic pollution. Okay. So this question, remember this thing. This a small correction in this question. So the correct answer is C. I hope this is clear to you. Okay. Hmm. Coming to the seventh question. Uh, the standard multiple fermentation, that is MPN. So what is this MPN method? Sorry, multiple fermentation test is on sample. Why this MPN test is done, I will discuss. I have made a separate session about 4 and 5 slide about this determination of MPN. But as of now, just remember that what happened that if your sample is contaminated with some kind of pathogens. So suppose you collected some sample water from groundwater or from river, so you wanted to check whether it contains some kind of pathogen or not. So to check the presence of any kind of pathogens or any kind of harmful microorganism present in the system, we do perform MPN test. And what happened that suppose if that and we use the concept of indicator bacteria. Just I'm giving you a small overview. I think before no, yeah, I will be discussing in last only because that will take a longer time because I have prepared separately prepare everything. So I will just just ignore this question for right now. I will be discussing this question at the end of the discussion also. Okay. So I am just moving forward because one should have a basic knowledge about this MPN and all this thing. Okay. So I am just moving forward. I will be come back again on this question. Okay, please don't worry. Okay. So this is a theoretical question. Zeta potential is the electrical potential between the shear plane and the bulk solution. So this statement is true, and you also do know that zeta potential is indeed the electrical potential between the shear plane, the plane at the which fluid velocity, and the bulk solution. It is important concept in collider solution. So what happened that this is, suppose imagine a colloidal particle is there. So what will happen that it on the surface of this colloidal particle there will be some kind of charges. So due to the charges it will create some kind of a potential around this surface, around its surface. So a potential is being created between this surface, that is in surface, and whatever the liquid solution present in outside that area. So this helps in a many way. It helps in the coagulation. And so what happened that suppose and I want to remove this colloidal particle. So first what I have to do, that we have to pass this barrier of zeta potential. So we will be adding some chemical in a such a way that it can uh, destroy this um, potential that is around this colloidal solution. Okay. So in that way, this is very important concept. I hope this is clear to you. So obviously, this statement is true. Okay, so there are mathematical. So if you must have gone through such kind of graph, maybe. So with time, this repulsion force and all these things. So this is all related to this zeta potential and all. Okay. Huh. Hmm. Coming to the ninth question, select the correct characteristics. This is multiple correct question. Correct characteristics of a coagulant required for a coagulation. So remember what? Why do we know? Why do we need a coagulant? So in your water, suppose there are many particles which are not being suspended, so we will be adding some kind of chemicals. The most common chemicals which are being used are, let me take out the notes, my notes. Hmm. Actually, when I was discussing, the most common coagulant is alum only. We use alum also. So what will happen that this alum will initially what was happening that when there was no chemicals added, this particle will remain suspended. The term we use, they are stable in the system. So by adding coagulant, we are destabilizing it and making it settle down. Okay. So remember, we are making something by adding coagulant, we are making one particle which was initially stable in the system, we are destabilizing it and we are making it settle down. The most common is alum, because the pH range of the alum, working pH range of the alum is 6.5 to 8.5. The most of the water which we collect from our groundwater or river water has a pH of this range only. Okay. Then the other another coagulant which is used is chlorinated coppers or Mm, huh. So it's a kind of iron chloride salt in presence of iron sulfate. Okay. Then some of they use also use hydrated ferrous sulfate also, that is FeSO4.7H2O. So but those iron salt has a working pH of very of the working pH is of very high. It generally works in a pH greater than around they work in the pH range of 9. So generally they are not used. Okay. So the most common which is being used in water treatment method is alum. Okay. But currently people are avoiding to use the use of alum, because this alum, presence of alum, suppose there is some limit of alum that it should be it should be, I think permissible limit is 0.03 milligram per liter. So if it is exceeding that amount, then it will cause some neurotoxin diseases. So what is this? It is suggested that people miss doing treatment plan. People are avoiding the use of alum, so they are using some kind of different coagulant. Okay. I hope this is clear to you. So there are different characteristics. So the first is non-toxic at working stage. Obviously, the your coagulant should be non-toxic, because suppose if you are treating something and now it is causing secondary pollution and you are providing to for drinking, so you are just causing more harmful to that person. So if I'm using alum in a very high amount, so obviously that alum will cause some neurotoxin disease. To this treatment method is not good. So correct. So obviously it should be non-toxic at working dosage. Okay. Should have high charge density. Okay. Sorry. First you can read this thing. It should have high. I will discuss one by one. So first I am discussing about the coagulant should not introduce harmful substances into water being treated. Okay. The second option is should be having a high charge density. So what do you mean by high charge density? Coagulants with high charge density are more effective in neutralizing the charge on the colloidal particle, affecting their aggregation and removal from the water. Okay, so facilitating their aggregation. So what happened that why those coagulants are, suppose in your water, what is happening? This is your one suspended particle, yeah, one colloidal particle. This is second, this is second. why they are not getting settled? Because they are not getting settled because their weight is not so high. So what will happen that we, and they obviously, I have already said that they have some kind of charge around them. So suppose it is positive at, remember this is your particle, and at every, all around this surface there is this thing positive charge. Okay, this positive, this positive, this positive, this positive. Okay, so now what will happen that, and similarly what will happen that this particle will have also positive, positive, just imagine this is positive. So obviously they will never interact with each other. So now what I have done, by adding some coagulant, I have changed the surface chemistry of this water. So what will happen that this charge will be removed from here, also this charge will be removed, and eventually what will happen that they will, form a larger particles, and its weight will increase, and eventually it will settle down. Okay, so that's why, to remove this charge density around this, charge around these particles, we will adding those chemicals which has very high charge density. Okay, should have, should be having a low no, it's this is also correct, this is incorrect. It should have high charge density. Okay, insoluble in neutral pH range. Obviously, I have already said that the groundwater which we collect from our river or uh, from river or groundwater has a pH range of 6.5 to 8.5. Okay, 8.5. So which is around the neutral pH range. Okay, neutral pH range is around 7. Okay, so our coagulant should be working in such a way that it should work in the pH range of 7. The coagulant are typically added in water at a pH range where they form insoluble particles. They precipitate, help in the emerging the in mixing the colloidal particles and facilitate their removal during the sedimentation process. Okay, so my main target is to make this suspended colloidal particle to settle down with the help of, by changing their chemical property, or by making them stick together anyhow. Okay, so this option is also correct. Soluble at in a neutral pH range. No, not it should not be soluble. Now imagine that you have added some chemicals instead of, working on those things. Now imagine that they have break. Now you have used as, you have used LM. So now what will happen that, suppose imagine, generally LM is very insoluble. So now, and what do you mean by soluble? It is dissociating in its individual species. So if I am adding LM, suppose I am, generally the LM doesn't have work like this. So now imagine you are adding a salt which is you are adding A and B, and after adding in water, it has converted into some kind of A 2 plus, sorry, and B 2 plus. So obviously they won't be 2 minus. Okay, obviously now what was the target was to act on the collider particle that is present in the system, not to dissociate themselves. So my main target will be, or my main objective which was there, will not fulfilled, and there won't be any kind of coagulation in the system. I hope this is clear to you. Okay, so the correct answer is A, B, D. It should be non-toxic at working dosage, should be having high charge density, and insoluble at neutral pH. Okay, A, B, D. I hope this is clear to you. Last question, which is also related to. See, if you have not gone through the concept of repulsion, compression, then this question might seem difficult, unfamiliar to you. But you have already gone through the question, which is a question note discussion, which was there in the system. No, sorry, on the portal. you can answer this question. Okay. Okay. So about this coagulation theory, the net, so there is some coagulation theory and it is being given by the net force on the colloidal part is repulsive at greater distance and become attractive only after passing through the minimum. Yeah, correct answer is A. But I will be discussing each and every option why A is correct and B and C is incorrect. Okay. The net force on the collider is repulsive at greater distance and becomes attractive only after passing through the maximum net repulsive force called energy barrier. The above statement is relevant to which of the following mechanism? Okay. So remember, suppose I will just discuss the statement. The net force on the colloidal particle repulsive is true. Okay. Why it is true? And it is not true means it is for ionic layer compression. And how, what is this ionic layer compression? In ionic layer compression, initially there is a repulsion between collider particle due to their surface charges. Remember what I was saying here, these two are of same charges. Either they will be having all over the positive charges, or they will be having some on the both side there will be positive see, condition is same for both the cases. So either they both of the particle will have positive charges or both of them will be negative charges. And we know that positive never attract each other, they will always repulse. Okay. They will always repulse. As particle approaches each other, the repulsive force dominates, leading to the formation of energy barrier that prevent particle to coming to the close. Okay. Close contact. So actually, right now I don't have just that picture which is being just remember no, I have not added that picture. So after the I will just open my class notes and I will just make you. I will just I will open after this discussion. I will open my class notes. From there, you can see that how this thing works. Okay. However, as particle gets closer, the compression of the double layer member occurs, reducing the repulsing forces. Now, what will happen that there when this energy there are different barrier in the energy system. Okay, now so there will be a double layer compression, and so as soon as the two particle will come, initially they were repelling each other, but now somehow I have forced them to come together. So what will happen that the compression of the double layer occurs, reducing the repulsive force. The double layer which was present in the system will get compressed, and the reducing force which was present in the system will also get reduced. Eventually, the attractive van der Waals forces between the particles become dominant, leading to the particle agglomeration. So I hope this method, this van der Waals forces, particle dominant, and all this thing is very clear to you. Okay, so I will just show you one of my lectures. I hope this is. Hmm. So remember. Hmm. So this thing I was saying that I hope my. Are you able to see my this PDF? Please confirm.
Yes, yes.
Hmm. This diagram you can see initially what was happening that these two were okay. So this is like this is how the how we generalize the this attraction and repulsion force. So what will happen that initially at it was at very distance, the repulsive force was acting, repulsing force was dominating, As soon as we start bringing them together, these particles are being bringing are getting together. So the repulsion force will be getting dominant, and the repulsive force will decrease, and the attractive force in the form of van der Waals force will start acting, and eventually what will happen that the particle which was initially in this range, and remember initially what was happening that all there was a this thing, the particle which was there, it was all around the system. As soon as they start coming closer, you can see that the layer which was there started to decrease. Okay, initially here in this case also you can see. So you can see that this layer has decreased. So as this layer has decreased means the distance between two particles has decreased, and the repulsion force has decreased, and the attraction force has increased. So eventually initially the particle was very stable in the form. Stable, you can see it was very stable. When I am talking about the stability, I am talking with respect that the colloidal was not going anywhere, it was just there in the system, and my main target was to make it settle down. My How can I make it settle down? By destabilizing it. So and how this is possible, how this by some means, and we are just either increasing the pH of the system or reducing the increasing the ionic strength of the pH or reducing the pH of the system. Okay, by some addition of some chemicals we are doing that. Okay, I hope this electrical and bundle wall force is very clear to you. You can see we have added how this chemical, when we add some chemicals, how this happens. So here they are talking, there are different method of coagulation, by either by when we are saying that reducing ionic strength, increasing ionic strength, or when we are saying increasing ionic strength, we are increasing the charge and something like that. Reducing pH, we are reducing pH. How actually if I start discussing, first you should know that how this pH system works. Okay na, then only we can say that, but I am not going discussion. So sometimes what happen that instead of using chemicals, people also use some kind of polymers. So what will happen that when we add some kind of polymers, so this colloidal particle all will get combined, it will form a single bulk thing, and it will get settled down. There are some, now there's see they have used some kind of chemicals coagulation, they have used LM. Okay, FeCl3 is also used. Here you can see that initially it was charged things. By adding this chemical, we have changed the characteristics of this colloidal particle. Now it will attract with another positive particle, and they will settle down in the system. I hope this is clear too. So this is a clear concept of, we are actually what happened that when we coagulate something, there is rapid mixing, and after that it will form some coagulate and it will get settled down. So initially you can see that initially the water was very dirty. We have added some chemicals, and all the particle which is there will get settled down, and eventually you will get clean water. So this is lab experiment. This is picture is being taken from our lab. Okay, I hope I'm just showing my class notes. I hope this is clear to you. I'm just to show these pictures. See here they have added FeCl, FeOH on FeCl3 they have added. So what will happen that if when we add FeCl3, it will react with the OH present in the system, and it will form FeOH precipitate. Okay, and similarly here you can see that they have used aluminum hydroxide, LM. They have used LM, that is Al2SO4 dot what is the formula of LM? Uh, Al2SO4 dot whole thrice dot 18H2O. Okay, so they have used that thing, and you can see this white precipitate thing has formed. Okay, I hope this is clear to you. Okay. Hmm. So the correct answer is A. So before discarding those two options, I will be also discussing this interparticle bridging. Okay. interparticle bridging. Just 1 minute. Hmm. So interparticle bridging. So in this mechanism, a coagulant, typically a polymer. So remember, when I was showing you the picture now, I hope you remember the pictures. In this mechanism, a coagulant, typically a polymer with long molecular chain, is added to the water. This polymer molecule can observe on the surface of the colloidal particle certain bridge between the. So if you remember, so if this PDF is still open, I will. So you can see. So they are creating a bridge between those particles. Okay. So what I am saying, this polymer molecule can observe on the surface of the colloidal particle, creating bridge between them. This bridge facilitates the aggregation of particles into larger flocks, which can settle out of the water. This mechanism does not directly relate to the this is other another thing. Okay, but I hope you have understand and how this is look. This looks like this. There will be some this polymer is very of high molecular weight, and it has long chain, so it will form some kind of bridge between them, and it will so you can see that finally it all three will accumulate aggregate into this larger flux, and it weight will increase and it will settle down. Okay. In in sweep the coagulant add in the aggregation of fine particles by providing larger, rapid settling. Sorry. In sweep coagulation, the coagulant adds in the aggregation of fine particles by providing larger, rapid settling particles, often called sweep flocks. These sweep flocks collide with the smaller suspended particles, causing them to adhere to the larger flocks. These larger flocks settle more rapidly out of the water. While this mechanism involves interaction between larger particles, it does not. So I don't have picture for this thing, but what happened that swift coagulation, how it is how it is just I will show you via picture. So now just imagine that in a water there is this thing. There will be larger particles, there will be a smaller particles, larger particles, smaller particles. Hmm. So what will happen that we will add some kind of particles, or we will do some kind of physical mechanism. What will happen that these larger particle will start getting settled down. As soon as they will start getting settled down, what will happen that it will also the a smaller particle. What will happen that this a smaller particle will get attached to it, or when they will be coming there, it will stick to this smaller particle, and they will similarly this will also when will coming down, it will stick to this thing, and both and now what will happen that this both will now accumulate in one larger particle, and then those particles will settle down in the system. So in a manner, just we are acting on the larger particle, we are not acting on the smaller particles, we are just doing some changing chemistry. I don't know exact mechanism how they activate this destabilize the larger particle, but somehow they destabilize this larger particle, it will settle down in the system, and as soon as they will settle down, it will also stick on the smaller particle will get stuck on the smaller particle, and eventually that both will settle down. So I hope you have clear about this thing, that is interparticle bridging, sweep coagulation. So the picture which I was showing you now is kind of sweep this picture is kind of a sweep coagulation only. So what will happen that a smaller particle, just I don't actually this kind actually right now I don't have any examples of this swift coagulation. So, but anytime you can check on internet that what is the example of this swift coagulation. Okay, I hope this is clear to you. If you have any doubt, apart from question number 7, which I will discuss at the end of the discussion, apart from question 7 till now, if you have any kind of doubt, you can ask. Now I will be discussing about the biological parameter. So remember different parameter which we were discussing. A chemical is like salinity, hardness, heavy metals. Physical is taste order. Biochemical is BOD. This is not POD. Then macrobiologically. So I will be discussing about this microbiological parameter. Remember when I was discussing this question, I discussed in a wrong way. But I hope they are talking. I hope you have understood that they are just asking that what is the different parameter, water quality parameters. Okay. So what are the chemical parameters? So salinity, yeah, sorry, salinity, hardness, alkalinity. Then this thing, what do we called? pH of the system is also a chemical properties. Then physical comes taste, odor, temperature, conductivity is dissolved. Then suspended solid. All these are physical parameter. Biological only it will be some amount of organic. BOD is not a water quality parameter. This question is I have taken from the previous year question of NPTEL. So this should be corrected. And microbiological is presence of some kind of pathogens, or when we are talking about volatile suspended particle, volatile means the one which contains carbon, and generally the organic matter which is present some kind of bacteria microorganism is in form of suspended volatile form. Okay, so that's why we are calling it microbiological and viral particles. Okay, so I will come to this question number 7 later, but before that one should have idea about microbiological concept. So if you have any doubt, please ask now. Out of those 9 questions, I hope everything is clear to you. I'm trying to explain each and everything with concept and trying to relate it with real world situation. So one thing, my suggestion is that whenever you are trying to read anything, just try to relate that thing to the real world situation. If you are if you are able to relate that thing to a real world situation, means you are going on right track. Everyone can memorize the formula, can solve the question, but relating that question to real world situation is little bit tricky thing. So always try to always try to, whenever you see things, just try to see that where those things are around me. Everything, whatever I have said to you will be is around you only. Okay, so and this the advantage of this environmental engineering department is that thing, you can directly relate those things with your surroundings, with your water, what is happening to your water, either your water is good or bad, you can just check it. Okay, so microbiological concept. So again, the first, what is this microbiology? Microbiology is the study of microscopic organism, that is bacteria, viruses, algae, fungi, and protozoa. So this is microbiology. Okay. So pathogens are microorganisms that cause a disease in human beings. So there are different kind of microorganisms. Some microorganisms are very useful to us, but some microorganism, if present or if we ingest somehow, it will come as pathogens, and that will cause some kind of disease, which I think everyone is known. I think everyone has idea of this thing. Okay, so one of the major tasks in environmental engineering to ensure that water used for human consumption is free from waterborne pathogens. Because see, remember, there are many diseases due to this waterborne pathogens. Okay, so and that is due to some presence of some pathogens. So now if you ingest that water or drink that water, you will suffer. So it is always made sure that your water is free from any kind of pathogens. Okay, so one main source of waterborne pathogens is human and animal excreta. I hope you have idea about about this, that whatever the waterborne disease that it is being developed is order either due to human or animal excreta. Consumption of the water contaminated with human or animal excreta thus may cause waterborne diseases. Okay, so how to ensure that water for human consumption is free from pathogens? It is very difficult task because you cannot measure each and every virus. You can, because there are hundreds of pathogens present in the water, so you cannot measure each and every pathogens present in the system, and you will say that this water is very is harmful to us. So water may contain different type of pathogens. Water sample must be tested for the presence of each of pathogen, which is difficult and time consuming and expensive task. So there are different kinds of pathogens, so we cannot, because that will require too much time, too much money, and it will also time consuming. So for a single amount of water, you cannot spend this much of water. Then that this will make your water treatment very inexpensive method. So we have to develop one such method that can say that if that we have to develop some method that can indirectly say that your water is contaminated. Okay, so people have developed some method. Okay, so I will be discussing it one by one. So people have come up with the concept of indicator organism, or that is coliform bacteria. So what is this indicator organism? Is say that like pathogens. So just read out the statement. It will be very clear to you. Clear to you. Like pathogens, coliform bacteria are present in the faces of all warm-blooded animals and humans. So all the animals, which is all the animals are warm-blooded and humans are there. They contain this coliform bacteria. The number of coliform bacteria present in the feces is in order of magnitude higher than the pathogenic bacteria. Okay, so what happened that this pathogenic number of this coliform bacteria is in much higher. However, the coliform bacteria are themselves generally not pathogenic. Remember, this coliform bacteria are not pathogenic. However, their presence in drinking water indicates that pathogens could be present. Now, suppose if you have tested one water, remember what was our what did I say? That main source is human and animal excreta. So, and all the waterborne diseases are due to this animal and human excreta. Sorry, human and animal excreta, and these excreta contains coliform bacteria also and pathogens bacteria also. So now I don't have any mechanism to measure each and every pathogen, but we have mechanism to measure coliform bacteria. So, but what is it is saying that if coliform bacteria is present in the system, means pathogens are present in the system. And we know that those pathogens are coming from the human and animal excreta. Okay, so however their presence indicate the pathogens could be present. It really sorry. However, the coliform bacteria themselves not pathogenic. However, their presence in the drinking water indicates that pathogens could be present, because both of them. Why it could be indicative things? Because remember, we are trying, we are not using confirm thing. Remember, we are very conscious about writing this statement. Indicates pathogens could be, not for sure. We are just saying could be. It is relatively easy and expensive to test for coliform bacteria. So now remember, if suppose two things are coming from the same source, and and this source contains many things. So see, this is simple coliform, but this is pathogen, and pathogens can be of any types. And we know that measuring this is very difficult. So what will happen that, and we have techniques to measure this coliform, and we know that both are coming from the same source. So if this is present, then this might be present, not present, must be present. I am saying could be. Just remember, be cautious about this statement that if indicator organism is present, pathogens could be present, not for sure it will be present. Okay, so it is relatively easy and inexpensive to test for coliform bacteria. So if coliform bacteria are found in the water may contains pathogens. Again remember, may contain, and hence is unsafe for drinking without in disinfection. Sorry. Huh. without disinfection. And we know that in last class we have a study about the disinfection, that is use of chlorine, ozone, UV. Okay, water not containing coliform is unlikely to contain pathogens. Okay, so but you can say if the coliform is not present, you can say that it is very rare that some pathogens will be there. Okay, so there are several techniques that will confirm this. This could be also can be, just ignore what I said. I hope this is clear to you. Okay, so both thing is, you should remember why this coliform bacteria is chosen. Why it is chosen? Because it is present in humans and animal guts. When the excreta contain pathogens also coliform, and so if the coliform is present, pathogen is present may present. So this is kind of just a indicative organism. Okay, I hope this is clear to you. So what is total coliform, fecal coliform, and E. coli? Okay, the total coliform. So remember, this is the shape of E. coli. The total coliform, fecal coliform, and E. coli are all the indicators of drinking water quality. The total coliform is the large collection of different kind of coliform bacteria. So all the fecal means all the coliform which is present, fecal, non-fecal, is termed as total coliform. Okay, the fecal coliform are the type of total coliform that mostly exist in feces. Okay, the excreta which humans and animals produce, the coliform present in that is known as fecal coliform. Okay, E. coli is the sub of fecal coliform. E. coli is a sub of fecal coliform. One strain of E. coli is pathogenic. Presence of E. coli in the water indicates the recent fecal contamination. Okay, so if E. coli means, there will be some different tests. We will test for coliform also, E. coli also, and if E. coli is present, then we can say. So this was just kind of a general knowledge, this last statement. Okay, but you should focus on this thing, that a total coliform is summation of all the coliform present in the system. Fecal is only due to fecal, and huh. So and E. coli is kind of indicators. E. coli is a subgroup of fecal coliforms. Okay, E. coli represents that, because what happened that, why we are saying that recent fecal contamination, because if after some time all the E. coli will either die. I don't know, you can check in on some standard book, what happened to E. coli after some times, because after 1 day 2 day, as far as I know, all the E. coli which is will be dead after some time due to some mechanism. So that's why if E. coli is not present, we will be saying that the fecal contamination is of past, means it has happened long time ago. But if E. coli is present, we will say that the fecal contamination is present in water, and that has happened recently only. Okay, so I will suggest you to go and check on this, what happened to the E. coli after some time. Right now, as far I know that all day, but all died due to some mechanism, but I might be wrong also. Okay. So testing for the coliform bacteria. So obviously I have said that there should be some testing. The testing is, one method is serial dilution technique. Okay. Serial dilution technique. Often the bacterial contamination of water in high, what will happen that your bacteria which is present in there, this E. coli is present in there. Remember, I am, because those are in rod shape. Okay, so that's why will have very high amount. Okay, so what will have very high amount. So I have to dilute before testing it. I have to dilute it. Okay, often the bacteria contamination in water is enough to require dilution before enumeration by standard techniques. So there has been several standard techniques. Water samples are diluted by serial dilution technique, which is illustrated in the following figure. So what will happen that initially this will contain your original sample, means that might contain some kind of pathogens or that kind of. So what will happen that I will take 1 ml of here, from here to here. So the dilution will be 1:10. Okay, similarly I am diluting 1 1 1 means 10 every time. from remember the volume of this will be around 10, will be no how any amount you can take, but generally 10 ml is taken. Okay, so from here you are taking initially 1 is to 1 ratio was there, means there is no all the means there is no any kind of, this is original solution. Now what you are doing, that you are taking 1 ml from here, 1 ml from here, and you are I hope you remember this dilution factor formula. I hope in initial classes when I was discussing about this order and what do we call taste and order, so we are discussing about this FTN, TON, and all these things are just nothing but a dilution formula. So how this dilution formula is defined? The volume of sample, I also forget. So how? Hmm, hmm. So it will be just let me check. It will be volume of sample, total volume, that is uh, volume of the sample plus volume of ultra pure water divided by volume of sample. Okay, sorry, remember this is so this is around dilution factor. Okay, I hope this is clear to you. So what I am saying, that here initially all 10 ml was my sample only. So now I did that, what I did that I take 1 ml from 1 ml of the sample plus 5 ml of 9 ml of pure water. So it will be 10 divided by 1. Okay, so dilution factor is 1, but here I am writing it in the form of ratio, that how much serial dilution I have done. So I have gone from 1 is to 1 to 1 is to 10. Just remember this dilution factor, and this thing is written in very different way. Okay. Okay, huh. So what will happen, that the first test tube in the cyst contains 10 ml of the undiluted sample. The 1 ml of the sample is transferred to the second test tube, which is already contains 9 ml of sterilized water or ultra pure water, which does not contain any kind of contaminant. The procedure is followed to obtain larger dilution. Okay, so we will be diluting till 1 is to 10 ki power 5 ratio. Okay, so what happened, that something called MPN theory is, now you have this thing, you have different kind of set, that is one set which does not contain, which is pure sample, then it the number of bacteria eventually has decreased by 10 ki power 5 ratio. Okay, so if it has contains if it contains 10 ki power x, then you can subsequently find how much, or either if I measure the coliform present in the this this tube, then I can find the coliform in the original by multiplying by the given ratio. Okay, so remember, so this MPN theory is say that let n be the number of organism in the sample. Okay, so remember that this the coliform can be found in the total three method. One is mathematically. See, in all cases we have to do perform some kind of experiment. Depending upon the result of experiment, you can depending on the result of experiment, you can find the MPN, by most probable number. So we are just trying to find the probability, but how much probable is that, probability that that coliform bacteria is present in the system. We are just doing that thing only. Okay, so actually I will discuss with time. So let n be the number of organism in the sample of volume VML. Therefore the average number of microorganism per sample is n by v, that is known as lambda. So if n is the number of organism in system of volume v, then the lambda will be given by Vn by V. Note this does not mean that every 1 ml of liquid will from the original VML sample will have lambda organism. Remember this statement. Okay. In fact, any particular in 1 ml liquid may have 0, 1, 2 or n organism. We are just discussing about the probability. Okay. The probability that any 1 ml liquid will have X organism is given by Poisson distribution. Oh, where does the formula? Just 1 minute. I think formula. I didn't have formula was written. Just 1 minute. Give me one minute. I'm doing. I did not saw it. Sorry for that. Just give me one moment. Okay, na? So I hope you can see my screen now. Hmm. So what happened that what I was saying that what I was saying that we know that this if n number of bacteria is n number of organism is present in VML of sample, then the number of organism per ml will be given by n by v, or that is being represented by lambda. But converse is also, you should also remember that this 1 ml of liquid from the original VML must may not contain n organism. So now suppose you have volume v, total volume v, and the total number of organism is n. So the lambda will be given n by v. But now suppose you have taken 1 ml of sample from here. We have taken at from uh, uh, when we have taken here 1 ml of sample from everywhere na. So it the number of bacteria that is the it might happen that all the bacteria which was there may not come out. It might happen that only one single zero number of bacteria has come, or one number of bacteria has come, or two number of bacteria has come. Then the probability that 1 ml of the elucate that we have taken will contain x number of organism is given by px lambda की power x e exponential minus lambda divided by exponent x, uh, factor of x. Okay, so I hope this formula is given. So this formula is clear to you. So this is just a MPN theory, that is most probable number, but that if I am taking 1 ml of sample, will there be any bacteria in present in that or not? So the probability that of any 1 ml one of 1 ml sample having no organism is given by means x is equal to 0, it will be given by e की power minus lambda, and the probability that 1 ml of the sample have one or more organism will be given by 1 minus e minus x. Okay, so now this is a mathematical model that now you have to this math this see this is a mathematical model. Now the question is how it can be determined the what is the number of bacteria present in the system. Okay, so that will be doing we will be doing by experimental method. So for the experimental method, we do something total coliform detection. Okay, so in total coliform detection, what happened that this is a MPN tube. Okay, so in many lab you this is a standard tube, but in many lab you have must have seen that simple test tube, and at the top of it a cotton is attached, and it contains some kind of uh, chemical that is known as I will be discussing what chemicals are being used in this experiment. Okay, so what will happen that just remember, just 1 minute. Huh? So there are several. Sorry, this broth is used. So broth is kind of a food for coliform bacteria. So what will happen that this broth will be this broth, which is known as L'Oreal Traptos, it will be T TADT में हूँ मैं हाँ नौ की बात करता हूँ मैं बैक करता हूँ हाँ हाँ ओके ओके मैं नौ की बात करता हूँ सॉरी फॉर दैट so what happened So what happened that we prepare one broth. This come in the form of salt form. You will be adding in there is some certain amount, some 35.2 ml of broth in 500 ml. So there is some standard method. So what happened that this broth act as a food for the coliform bacteria which is present in this is fermentation media which is suitable for coliform growth. The several test tubes with a small inverted tube is taken. So this a small tube is known as Durham tube. Okay, this whole is this whole tube is known as MPN tube, and this one this small I think hope you can see this thing. This is known as Durham tube. Okay, which is used in MPN test. Distributed in broth distribute the broth in test tube such that no air bubble is present in the small test tube. So this you have to insert in a such a way that this tube Durham tube does not contain any kind of gas. Okay, add 1 ml of sample to the test tube. Now what will happen that I will be adding some 1 ml of the sample in the test tube, because we want to check that how much bacteria is present in 1 ml of sample. Okay, put the cap on and let it incubate at 35 degree for 24 hours. If the media turns cloudy and gas bubbles are seen in inverted tube, the test is positive. So now remember, we have given them some kind of food. Okay, so that coliform will eat that food. It will eat that food and it will ferment it, and after fermentation it will release some gas, and that gas will be collected in the system in this Durham tube. Now what will happen that if coliform bacteria is present there, then the fermentation will occur, and that fermentation will occur and the gas will be released and that will be collected. So that will be a positive result that yes, bacteria is present there, that coliform bacteria is present. Now imagine that there is no coliform bacteria. So what will happen that no gas will be released there, no gas will be released, and your result will be negative. Okay, so this is overall of coliform detection method. Okay, Now remember, we are, if you are incubating for 35 hours, we are looking for total coliforms. And if you are incubating for 32 degrees, 35 degrees Celsius for 24 hours, then we are just looking for total coliform. But if you are incubating for 42 degrees Celsius, 45 degrees Celsius for 24 hours, then you are just looking for fecal coliform. Just remember this thing. This is for total coliform. Remember, the test is always done for two type of coliform. That is total coliform. Total coliform has temperature of 35 degrees Celsius, and fecal coliform has temperature of 42 degrees Celsius, 45 degrees Celsius. Sorry, I don't know why I'm saying 42, but it is for 45 degrees Celsius. Okay. If the test tube negative results is serial and then incubate, remember, what happened that it might happen that we are not giving sufficient time for the fermentation, so we will be giving more extra 24 hours just to confirm that yes, there is no bacteria present in the system. After 24 hours, remember here also we have already designed that this one is giving positive result and this one is giving negative result. But some of the in the tube which does not contain any gas, we will be adding extra 24 hours just to be sure that yes, no further bacteria is present in the system. Okay, I hope this is clear to you. So remember, what will happen that after some time, remember you can see this Durham tube contains some kind of gas. Means this is positive result, and suppose after 24 hours your tube is in this manner only. So you will be saying that you have got negative result. So you will keep it for extra 24 hours just to confirm your result. Okay, I hope this is clear to you. So so we are just giving you one example of this thing for river water sample. So what happened that we have take a river water sample and dilute the cereal in the 1:1, 1:10, and 1:100. Also prepare 9 fermentation tube with laurel traptose broth. Add 1 ml of 1:1 in all three tube, and suppose the result is shown in this way. So now what happened that you follow this procedure, and you find that you have taken for see, we do experiment in triplicate or five, we take five replica. Okay, so for same sample we have first dilution was 1:1, then 1:10, and then it was 1:100. It was seen then when 1:1 was happening, in all three tubes we get some kind of gases. Means three of them has given gases. So why all three? Obviously this was original sample, so obviously it was original sample, so it will contain some kind of bacteria. So out of but when the dilution was 1:3, so now remember that this was your original sample, 1:1. Now you have taken extra three tube, and you have added 9 ml of water in all these three things. And you have added 1 ml here, then 1 ml here, and then finally 1 ml here. So what happened that when you was initially taking 1 ml, so it contains some bacteria, so that's why it is giving positive result. But for second third time when you have taken 1 ml, the presence of bacteria was very less. So this is called probability, that if we are extracting some kind of samples from the system, what is the probability that it will contain some bacteria. So we are finding that thing. Okay, so similarly when we are now what will happen that from this tube I am diluting it again 1:1, and it was seen that in all three cases no gas was seen. So it was giving negative results. Okay, so to calculate the mpn value we will be using that concept. Remember, what was our formula? That if it is giving positive result, that it will be expressed, if bacteria is present it will be 1 minus lambda. If it is not present it will be exponential e minus lambda. Okay, so what happened that for this 1:1 ratio, all three was giving positive result. So it is 1 minus exponential e minus lambda. But when the ratio was 1:10, means your lambda has converted into 0. Initially for here the lambda is lambda, but for this case lambda is 0.1. because we are, how we are defining lambda is number of bacteria per, or per total volume. So in case only one was positive and other two were negative, okay. So what happened, and for all three cases this all three was negative, so we are writing in this form, that is exponential e minus 0.001 lambda cube. So you can, now what you can do that you can use the excel sheet to plot between p lambda and this expression, and you will be getting this kind of graph. You will be getting this kind of graph, okay now. You will be getting this kind of graph, and the the highest value which we will be getting is around point 0.27 per ml. So we will be reporting our answer that most probable number per 100 ml is 27, okay. Means per 100 ml of sample, if we take 100 ml of sample, there is a probability that 27 bacteria will be present there, okay. I hope this is clear. So this is a theoretical way to calculate your MPN. So alternatively, there is one another formula which is given by Thomas formula. The Thomas formula is given by number of positive tubes. So here, what is number of positive tubes? 1, 2, 3, 4 into 100 divided by ml of the negative sample. Ml of negative sample. How will we miss in how much this was negative? So remember here it was all 10 ml was sample. Here only 1 ml is because I have taken 1 ml of sample. So 2 ml, and here all three negative means 0.0, sorry 0. Here 0.02. I will explain in the later example how you have to. But you can use this formula to find the MPN of your system. Okay. Okay. I hope this is clear. So I have told you two method. One is use of this formula, that this expression, and then Thomas formula, and there is again one method, that is use of MPN table. So before going to the question, I will be discussing this question, that experiment was done, and it was they here they have performed experiment in. I have shown you example of triplicates, but here you can see that they have performed experiment in five five tubes. Okay, so 1 ml when the sample of size was 1 ml, it was four were giving positive, one was giving negative. When the size of sample was 0.1, one was positive, four was negative. When the sample of size is this much, remember you can calculate the sample size when you are diluting your sample. So what I was saying, when 1 is to 1 was saying we are taking 1 ml of sample. When it was 1 is to 10 ratio, the volume of the sample is 0.1. When it is 1 is to 100 dilution ratio, the size of sample is 0.01, okay. So the number of positive, this was result was observed. So we know this Thomas formula. So we will be noting down the number of positive tubes, that is 2 plus 4 plus 2 plus 1, that is 7. Then the ml of negative tubes, negative tubes we can multiply it 1 into this, 4 into 0.1, 3 into 0.001, 5 into 0.0001, and you can find the total number of negative tubes. You can also find the total volume. The total 5 tubes were used, and this was size of your sample. So you total this will be volume, and your MPN will be 247 per 100 ml. Remember, per 100 ml. That most probable means, suppose you have taken 100 ml of sample, there will be there is a probability. Remember, this is most probable number. This is complete probability, not sure. You are just probable. So there is, after this there is something called confirmation method. So this is just preliminary test that yes, bacteria is present. For confirming it, you have to do further experiment, which I am not going to do. But for biological, I will request you to go to check in the standard books. So there, what are different techniques? Like first is coliform test. That is preliminary test. Then there is a confirmation. Why I am saying preliminary? Because this is just a probable number. Yes, that this much amount of bacteria will be present. We are not saying anything about yes, it is present. We are just saying probable number, most probable number. Okay. So I was giving just example. So I was just giving one example. So I am just giving one another examples for my class notes. Okay, so the which I have solved, and I have just taken photo from that thing. Okay now, so three samples were taken: sample A, sample B, sample C. Just forget these two sample. I will just focus on sample A. So when sample, and total three tubes were taken. Okay now, it's not written here, but total three tubes were taken. So when the sample volume, here we have taken large amount of sample, that is 10 ml, remember. So when the sample size is 10 ml, two were giving positive results. When the samples were taken one, only one tube out of three, only one tube was giving positive result. And when the sample tube was 0.01, two were giving positive results. Okay. Okay, so now you have to find this mpn value. So I will be using first method, that is Poisson's distribution method. We know that out of three, positive, positive, negative, positive, negative, negative, positive, positive, negative. So we will be putting we know the formula which I have already said. We will be putting the expression here. We will be simplifying it in this form, and I will be plotting it, and I will be getting this kind of graph. And from graph I can say that the maximum value. See, we are finding most probable number, means max. Actually, to find this lambda, you have to find the maximum value of, means, uh, this p, wherever this p lambda is there, for that value we have to find our the wherever this is p is maximum, for that value of lambda we have to find, for that lambda we have to find. So best way is to plot plot the maximum. You can see, also this I am saying just approximately. So at 0.27 you can see, for lambda is equal to 0.27, the our my p lambda is maximum, so mpn will be that thing. The second method is I will be using so the third method is, second method is this use of formula, number of positive tubes into 100 divided by blah blah blah. From here you can see that we are getting mpn per 100 ml is equal to 249. Okay, so actually I have done some mistake here, because here you can see here per 100 ml is 27, but here it is 249. Some mistake has been done. Okay, so I am just giving, I can just find also what I have done, what mistake I have done. No, I won't be going to. The third method is use of mpn tube table. Okay now, so there are several mpn table. Okay, I will just show you mpn table. So this kind of ambient table are present in the market, not market, in the, what do we call, in website. This is ambient table. So my condition was that I am using a 10 ml, 1 ml, and 0.1 ml with 3 tube. Similarly, when you will be using 0.1, 1, 0.1, 0.1, then different kind of table is used. And in this table, what we look at the number of positive tubes, and we form a code. So we, from here you can see that two two positive, one negative, one positive, two positive, then the code of this sample will be 211. Okay, and from this table I will be going to 211, 211, 212, and you can see it is 0.27 mpn. So I will be reporting my answer as 0.27, 0.27 per ml, and per 100 ml it will be uh, 27. So from this result and from this result I am getting 27, means I have done some mistake here. I'm just giving you one. Oh, actually the mistake which I have done, I have taken here 5 tubes, but I have to take only 3 tubes. See, no, sorry. I have to, so miss, I might have calculated in a wrong way. Okay now, but I hope you have got the idea how this mpn is calculated. Okay, so after this there is one more preliminary experiment, that is use of this heterotrophic plate count. We provide some food to bacteria, and it will form some kind of what do we call it, a colony, and we will count it. So it is also kind of a preliminary test. This will just confirm that yes, this bacteria is present, and it has formed some kind of colony. Okay, so this was all for today. I hope you have understood it, and if you have any doubt, you can ask it, or I will end the lecture because it's 9 9 p 9 p.m. If you have any doubt, just let me. Hmm, how to get it? Hmm. If you have any doubt, please raise your hand or you can ask. Please share some. Okay, okay. I will share some question of alkalinity. I will share on that email that you have shared last week. And sorry, I have shared this time. Actually, I was busy with some of my work. That's why I could not reply you on the time. But this time I will make sure that I will share it by maybe tomorrow or day after tomorrow. So if you have any doubt, you can ask, or I will be just ending the meeting. Thank you for the joining. I am just ending the meeting. Thank you.